He gets started again, so. Can everybody hear that? Okay, I can. Okay, if sound levels are measured to exceed OSHA standards, should there be mandatory oversight by NASM regarding hearing loss prevention? Use your keypad to answer. We will have to program it in, but we can't add that in right now. Take about 5 minutes to fill it in. Okay. Give you a couple of more seconds to answer that one since people are still drifting in. Okay, Bob. 61% agree that NASM should regulate or have oversight of hearing loss prevention in that case. Next question. If sound levels are measured to exceed OSHA standards, should NASM music faculty disclose this information to students? And remember, these are anonymous. Except for keypad number 37. We know who you are. Okay, Bob. 83% believe that that should be disclosed to students. Okay, next question. If sound levels are measured in public school band programs to exceed OSHA standards, should music education faculty disclose this information to parents? Okay. Even larger percentage. All right, we'll continue with the presentation.
Welcome back, y'all. A couple of questions that came up during the break. I guess worthwhile mentioning to everyone just because I think they're good questions. The first one was with respect to the audiogram and the hearing loss. One thing that we kind of assumed and we kind of skimmed over, but it happens to be the case, whether you're a bass player or a piccolo player, the hearing loss is on the right-hand side of the piano keyboard. In other words, that notch that you get at around 4,000 hertz, the top end of the piano keyboard, very similar whether you're a bass player or a piccolo player. The other question is that the Brian Moore tape that you heard of the music through hearing aids, and it sounded pretty lousy. And of course, we want to prevent hearing loss whenever possible. But the last 2 years of our life, the only thing I've been really working on is trying to find out what parameters in a hearing aid are ideal for music, never mind speech, but just music. And there are hearing aids out there now with the correct parameters to optimize the sound quality of music, to minimize the distortion. And so this is something that I think for those of you that are considering hearing aids, for those that are a little bit older, or maybe know somebody that is in the music venue that requires hearing aids, what our understanding of them has improved dramatically in the last several years. They're not the old hearing aids they used to be. That's two general questions. So monitoring. Now what I wanted to do is turn around to the fourth issue. So we have the moderation, which makes sense in any sense. It's not just hearing. The humming, the elicitation of the stapedius reflex. Again, we're not sure exactly how much that affects, but even if it's 3 or 4 decibels, we've effectively halved the damage, cut the damage in half, and 3 decibels is barely perceptible. Improved monitoring is always a big thing. An example that I didn't talk about really is if you're in an aerobics class or a dance instructor, I'm not so concerned about the person that is there 1 hour here, 1 hour there, but I'm concerned about the aerobics or the dance instructor that is there for 6, 7 hours a day, 5, 6 days a week, and it's that constant thumping and everything. If we turn up the bass a little bit on their music, they still have that same thumpy thump, to do all the aerobic stuff with, but the overall volume level, the level coming out of the speakers, is much less intense, less damaging, even though everyone in the room thinks it's just as loud by turning up the bass. And that improves the monitoring. So there's a few little tricky things we can do. So now I'd like to turn my attention to the fourth topic, which is environmental changes. The first one is speaker amplifier combinations should be elevated from the floor. Now, all too often we see these big speakers and they're on the floor, and that's fine and dandy. And many of them are actually designed to be in contact with the floor. But what happens in that situation is the sound that's coming up through the speaker, it's lazy, like all of us. It has to make the life decision. Will I go out through the speaker cone and out into the room, or will I go into the floorboards? So it comes along and kind of looks around and says, I'm going to take the path of least resistance. I'm lazy. And if it's right on the floor, there's a good joining or good coupling of the speaker with the floorboards, and this low frequency sounds will go into the floorboards, thereby lost to the audience. The mid and the high frequencies go right out into the audience, no problem at all. What happens when you lose the low frequency sounds, which gives you the perception of the loudness, is that the first thing you do is turn up the volume to compensate, uselessly in many cases. This is a curve. Can you see the red at the back of the audience? It's a little bit difficult to see, but what this curve shows you is that around middle C, you've lost about 6 or 7 decibels of energy. Now, by the time you're an octave or 2 above middle C, the sound gets through very effectively. But all this left-hand side of the piano keyboard is lost through the speaker if it's in contact with the floor. So if you can elevate the speaker a little bit, or even tilt it up, aiming to where the listener wants to hear it, that low frequency sound will stay in the speaker, go out into the room, and not be lost to the floorboards. So the first thing that will happen in a case like this is that you turn up the volume to compensate, because you've lost the left-hand side of the piano keyboard, and you've increased the overall intensity, thereby increasing the overall damage. Elevating speaker, you know those little pink erasers we used to throw at our friends in grade 4? Yeah, well, find those little pink erasers. It doesn't have to be high-tech. Put them under the 4 legs of a speaker to elevate them off the floor. Those same low frequency sounds would come into the speaker and say, should I go into the floorboard or out to the audience? I'm seeing now a high impedance pathway. I'm off the floor now. I'm elevated because of these rubber legs. And these same low frequencies that are lost to you in the audience will now go out into the audience. Not only will you get a flatter response, but the overall level you adjust the volume control to will be lower, less damaging. Low tech. Second, stringed instruments should always have at least 2 meters of unobstructed space above them, for those that are not Canadian at 6 feet. Many pits, orchestral pits, are poorly designed. And what happens is that pit overhang will eat up the higher frequency components of the violas and the violins. Now, this is not a big issue for the woodwind instruments. It's not a big issue for the trumpet players and other brass, but it is a big issue for the viola and the violin. When a viola player or a violin player says, that's a great sound, what they're actually referring to is that the relationship between the lower frequency fundamental energy and the higher frequency harmonic overtone energy has a certain balance. And when they say that's a good sound, that's what they mean. When I play my clarinet, though, as a woodwind player, when I say, that's a good sound, I'm referring to the lower frequency interresonant breathiness, the low-end stuff. I don't care about what's happening in the high end. Yes, I may be able to generate as much high-frequency sounds as a violin, but as a clarinet player, I don't really need to hear it. So I've chosen a good instrument as a clarinet player so that when I'm old in grade 2 or 3 years from now, when I get a high-frequency hearing loss because I'm over the age of whatever, I'll still be able to enjoy and play my clarinet. I won't be any better, but I'm pretty shitty now. But a violin player and a viola player, they do need to hear that higher-end stuff. So if you place a viola player or a violin player under a poorly constructed overhang, usually which has some rudimentary acoustic tiling in the ceiling of it, and it tends to absorb the higher frequency components of the violin and the viola. So what does the violin and viola do? By the way, you see it there, the red one on the top is the normal spectrum, And then when they're under a poorly constructed overhang, you get all this loss of energy. So a viola player and a violin player will start playing harder to reestablish the higher frequency components. And in doing so, the person next to them has to play harder, and the person next to them has to play harder. Before you know it, the whole intensity level in the orchestra is needlessly high. Also, they'll be in our office a couple weeks later with wrist and arm problems. So that it's not just a hearing problem, it's how the whole ergonomic problem. If Mozart were alive today, I'm sure he would agree with me that all the viola players and violin players should be out in front of the overhang, or put them in a different room if you can. You can hook them up with electronics nowadays. But certainly they should have improved monitoring, and they should not be too close to an absorbing, high-frequency absorbing device such as an overhang. So get them out front and put the woodwinds and the brass in the back. That's a local change, or a positional change for musicians. 3, there should be a couple of meters of unobstructed floor space in front of the orchestra, and this is also in the classical domain. If you can back the orchestra, whether it's a high school band in a multi-purpose room or an orchestra on a stage someplace, if you can back them off the lip of the stage by about 6 feet, what happens is that the sound of the orchestra not only goes to the back of the audience, but it also hits the lip of the stage and bounces back. Now, not all sound bounces back. There's something called the pinna effect. Everyone do this. I'm going to talk now, and then I want you to cup your ears. In fact, let me turn off the microphone so you're only getting the sound from the front. Okay, now, this is just my normal voice. I want everyone to cup their ears like this and see if you hear me any more clearly when you do that. You might want to take it off for comparison and then put it back in again. Too bad we don't have a camera on you guys. It's kind of bizarre. Now, how many people heard better when they did that? Okay. How many people didn't hear better? Okay, those people that didn't hear better, it's a good chance you have a high-frequency hearing loss, and you should see your audiologist. There are other reasons as well, but if you did hear better, the reason you're hearing better is that not only is my voice hitting your ear, but the hand and the pinna together here. The pinna is this little sticky thing out on the back of the ear. It acts like a mirror, and it reflects the sound into the ear, so you get double the dose of the sound. But that's only for the higher frequency sounds. So when we say, and we do this, there's a good reason why we do this. So what happens is that the low frequencies have a long wavelength, and they just go right through into the floorboards, lost to the audience. They don't reflect at all. Higher frequencies have a shorter wavelength, and these higher frequency sounds on the right-hand side of the piano keyboard love to reflect off things. Actually, let me demonstrate something. Okay, what I'm going to do, just to show you with speech, that low frequencies, vowel ah, for example, ah is a low frequency sound, very little high frequency sound, whereas the consonant s is quite high frequency. It has energy out around the top end of the piano keyboard. Well, I'm going to go out in the hall, and I'm going to say a word, and probably you'll be able to hear it very well, but it'll be interesting to see what happens out there. And of course, I'll disconnect myself. Quiet. Okay. Should see an audiologist. But the idea is that you'll always hear the lower frequencies. They get through walls, they get through anything unaffected. They're small, they're long wavelengths, and they get through anything. Whereas higher frequency sounds, the treble notes, the harmonic stuff, they bounce into walls and they get lost. They don't get through very effectively. And that's one of the reasons when you do this, the lower frequencies do hit the ear, but they go right through to the wall behind me. They're not reflected. The higher frequencies kind of hit this door like there and just reflect in here. They don't get through to the other side. Okay? So same with this issue here. The floor acts like a mirror, a reflector for the higher frequencies, the the S's, the right-hand side of the piano keyboard, and enhances that. So what happens is that the orchestra on stage doesn't have to play quite as loud to get that same high-frequency element at the back of the audience. And showing the curve there, and again, the red's not showing up particularly good, but what that says is that at around the mid and the right-hand side of the piano keyboard, you can get 5 or 6 decibels more amplification that's done after the stage, so that up on stage it doesn't have to be quite as intense for it to be more intense at the back of the audience. So you don't have to play louder so the person at the back of the audience can hear as effectively. And if that's the case, bless you, the person up on stage will have less exposure in their immediate vicinity. And again, if we can reduce the playing intensity by a mere 3 decibels, which is barely detectable, we've effectively 1/2 their exposure, or doubled the time that they can be exposed before damage occurs. And the fourth one is treble brass instruments should be on risers. In other words, put trumpets on risers. This is the same sort of reasoning. What happens with the trumpet? Incidentally, with the trumpet, most of the more intense elements of a trumpet happen to be in the higher frequencies anyways. The lower frequency sounds coming out of a trumpet, they leak out all over the trumpet. If I was there with a sound level meter, measure the lower frequency note of the trumpet right in front of the trumpet, 45 degrees above, beside the trumpet, above the trumpet player, not much difference in intensity for the lower frequency sounds. However, for the higher frequency sounds where there's a lot of potential damage, a lot of intensity, it's much more like a laser beam. The sound kind of rattles around and sees the trumpet as kind of a guide for this high frequency stuff. So the stuff comes out of a trumpet much like this laser beam here in a straight line. And so all the damaging elements of the trumpet literally come out in a straight line. So if I can put them on risers, all that damaging energy goes over the heads of those downwind. It's as simple as that. So if you put trumpet players on risers, all the damaging energy does not affect those other people in the orchestra. And trumpet players are macho anyways. You know, they like to be seen, so putting them on risers make them feel really good. Trumpet players are really weird, eh? Oh, so why do you instantly dislike trumpet players? And the answer is, saves time. That's a no. I'm sorry. I like trumpet players personally. Any trumpet players here? Oops. I'm a white belt in karate. So those are 4 very simple sorts of things. There are other environmental strategies you could do. For example, if you find yourself in a classroom where there's a blackboard behind you and you're conducting it or working with an orchestra or a band, the blackboard is one of the worst things you can have behind you, because not only do you get the incident sound from the orchestra or the band, but you get the reflected sound coming off the blackboard to your head the second time around. And we've recommended many cases of I-beams, curtain rods, where you can pull some heavy curtains across the shiny surfaces of the blackboard when you're not using it during playing. So at least you get absorption of the reflected sound, and it cuts down the level for the conductor. And then you pull it open when you want to draw your staffs on the board and all the notes on the board. So there are a lot of very simple things you can do to any music room that are very inexpensive and makes good science and audiologic sense. Now, so far, I haven't talked about the obvious thing, which is hearing protection, which Elliot Berger will be talking about next. But before I give up the floor, are there any questions at all? Well, why don't you go to the microphones? While you're walking there, I'll have a bite of this chocolate chip cookie.
When you were telling us about putting the rubber erasers under speakers, would that be true for vocalists that use monitors that are down at the floor level? Would that assist them in not over-singing because they would get better feedback?
Yes, she was asking, of course, about the rubber erasers. Would that be good for monitors that are down on the floor? Yes. Not only should the monitors be elevated, but it's okay to aim the monitor to the singer, because what happens is the higher frequency components of the monitor are like the trumpet. They come out in a straight line. So if you aim it right at the person's face, the overall level needs to be much quieter. Good question. Thank you.
What about the use of those polyurethane baffles, sound baffles, between sections in an orchestra?
The question is about these baffles. Some are made of wood, some lucite polyurethane, different materials. Baffles can be very good. The only problem with baffles, or only limitation with baffles, is that they have to be within 7 inches of the ear in order to have any great effect in most music rooms. This came from a study in the Performing Arts Medical Association journal, PAMA, in Camp and Horseman in 1992. and they put baffles in various locations, and they found that you could still get 13, 14 decibels of high frequency lessening or attenuation of the sound, which can be very useful, but the baffle had to be right up against the back of the person playing. And this does limit certain instruments like the violin that has a lot of movement. It might be very good for the clarinet player. The problem is if it's further away than the 7 inches, you are not only getting the incident sound, but you're getting the reflected sound off the ceiling, off the walls, and off the floors and other structures in the room. So baffles may have some limited usefulness if they're not very close to the individual's ear. Okay, well, thank you. One last point, for those that are interested, there's a website that I noticed isn't in your handouts from the Musicians Clinic, which is actually a lot of fun. It's kind of written with the college or university student in mind. It's not a downer. It will never say, don't do this, don't do this. It will say, do it, but this way. And it's www.musiciansclinics.com, plural for the word musicians and clinics, one word though, .com. Great, thank you.
Hello, everyone. My name is Elliot Berger. I'm a senior scientist for auditory research at a company that manufactures hearing protection devices. And I've been working in this field for better than a quarter century and have a lot of interest about this topic of hearing protection. Don't often get to talk to music groups, so I'm excited to be here and share with you some of my interest in this topic area. Before I begin, I just want to alert you that in the binders you have a copy of my PowerPoint slides. Unfortunately, some of them didn't print too well, so a couple of the graphs, if you want notes, you may need to mark them next to them. In addition, if you still have your plastic bags with you, there's some goodies in there that accompany this lecture. There are 2 pamphlets that have a colorful cover on them. One of them is about a 12-page brochure. It's called Life Can Be Loud. And it's a general pamphlet on the effects of noise, the importance and excitement of being able to hear well, the use of hearing protection devices, and some other related materials. And it's loosely correlated with some of the topics that I'll be discussing in the presentation. There's another document that I made just for this lecture here today, which is called, the title of my lecture, What Musicians and Music Educators Should Know About Hearing Protection. And if you open that up, you'll find a series of references. There's many articles that have been written about the effects of music on performers and listeners. I've selected some of the ones that I thought were more relevant to our interest today. They're listed on the left-hand side of that. You'll also find a listing of recordings and videos that you might find relevant, some web links, and information on how to purchase hearing protectors. I'd like to mention in particular the second web link, which is the one that I maintain. Has a number of other materials on hearing protectors, a series of articles called the ear logs, and there's 21 of those that you may find useful pertaining specifically to issues of hearing and hearing protection. So you might wish to visit those at your convenience. You'll also find something particularly relevant to my topic, which is there should have been 2 earplugs in your bag. They are foam earplugs, so they are not necessarily the type that are most apt for musicians and music-related venues, but they're very effective hearing protectors. And one of the things that you should be aware of today and take away from here is that not only might you wish to protect your ears when you're playing and listening to music, but there's many other times in life when you might wish to protect your ears, and those foam earplugs can do a very good job for that. So there's some samples in there that I'd like you to be aware of. We've been listening today to my colleagues talk about noise, its effects, how to protect ourselves from it using other types of strategies, and what sort of regulations might be involved in the noise area, in the music area and in the noise area. And of course, music is just one of the forms of sound that might potentially be damaging to our ears. We live in a world that's awash with sound. The world is really, in my opinion, much too noisy a place, not only from noise hazard, but in terms of noise annoyance. Many have pointed out the value of quiet for soothing the soul and allowing introspection and rest. So there's not just issues of noise hazard, but noise annoyance as well. Before I proceed any further, I'd like to just ask you a couple questions about your experience with hearing protection. So number one is, have you recommended the use of a hearing protector in a rehearsal or performance setting? So how many of you have talked the talk that we're going to talk about today? So better than half of you have recommended the use of hearing protection. Now I'd like to see how many of you have walked the walk. Let's take a look at question number 2. Have you ever worn a hearing protector when performing or listening to music? So how many of you have set a good example for your students or others? Interesting, about the same proportion. So presumably those of you who are recommending them are the same group as those of you who are using them. And the others who aren't answering yes to those questions, perhaps we can influence you some with today's discussion. So this topic is going to be all about hearing protection, and I'm going to review the types of hearing protectors. I'm going to talk briefly about how they work, how we measure their performance, and then I'll give you some examples of the various hearing protectors that are available today. When we categorize hearing protection devices, we can normally put them into 2 camps: earplugs on the left side and earmuffs. Helmets are another category in the earmuff realm. Clearly, the earmuffs and helmets are not something that's suitable for music performance. You would look a little bit out of place with your tuxedo and your military flight helmet on stage. I'd also probably suggest that the semi-insert devices, which are these banded devices down here, are also not quite apropos. So we're really limited to the earplug type of devices, those first 3 rows on the left side of the slide, and I'll be presenting those in a little detail. In particular, I think I just lost my sound there for a moment. I'm back. In particular, I wonder if the batteries, are you losing the sound the same way I am? I'm hearing it go in and out. Maybe I need to change batteries? Okay, well, we'll see what happens here. The categories in those earplugs that are really the most prevalent today are the foam plugs, the pre-molded plugs, and I'll also be talking about the custom molded earplugs as well. The foam plugs were introduced in the 1970s. Is when they were invented and brought to the market. The reason that I point them out here is because they have become the most prominent form of hearing protection used worldwide today. There are many brands and varieties. You see there's all sorts of colors and shapes. What I would point out with foam earplugs is that they tend to be the most protective and the most comfortable, but that amount of protection may be more than you want in many music situations. I'd like to just point out that although there's all these nifty shapes, the principal value of the shapes and colors is to get people interested in wearing them. There isn't really any shape to a foam plug that's going to make it work better. In fact, if you look in the middle of this slide, the foam plug that was introduced first and patented initially, the classic yellow foam earplug, which you have in your bags, has really not been improved upon in the last 30 years. It's a simple cylinder, and for a piece of foam, that's all you need. The other shapes are really to induce people to be more interested in wearing their products. In fact, some shapes can be deleterious in that if you don't properly shape it, it can fit your ear less well. The other categories from that first line chart that I showed you are the pre-molded earplugs and other types of foam, and you see here. There are foam plugs that have stems in them. There are various ways of putting soft, flexible flanges on earplugs so that they can be slid directly into an ear. We've heard about custom earplugs, and I'll be more about those in a few moments. In addition, I'm going to talk about high-fidelity hearing protectors. Many of you are probably familiar with the ER15 series of products, which are built into custom ear molds. There are also less expensive ones which are built into pre-molded shapes. And briefly, I'm going to mention a product. You see an earmuff worn here, and that is an active noise-reducing earmuff. And that's a topic that's of interest to many people these days because it seems like hyper-science. We're going to bring all our electronic and digital technology to bear to cancel sound. And I want you to know what the merits and advantages of that type of product might be. We've seen diagrams of the ear today. And here again, we see a cross-section of the ear. You're familiar with the major components in the ear as we proceed from the ear canal to the eardrum across the ossicles to the inner ear. The reason that I put this slide up is that the principal way in which we hear our own voices and the sounds around us is through this air conduction pathway. But there are other pathways to the ear, which are the bone conduction pathways, and those are sounds that cause vibration of the skull and the tissues of the head that can directly stimulate this inner ear, and they bypass those external ear, that ear canal pathway. The reason that that's important is twofold. Number one is that creates the limit to the amount of protection that we can obtain. Normally in music, you don't need to worry about very, very high levels of protection, but if you are looking for maximum protection, the bone conduction pathways limit you to about 40 to 50 decibels. You can't block any more sound than that by occluding the ear, because then the sound gets to the inner ear via these other pathways. The other importance of the bone conduction pathways is that when we seal the ear, and we'll listen to this in a few moments, we do something called the occlusion effect, and we change the effectiveness of those bone conduction pathways, and those are the pathways that add the fullness, the warmth, the bassiness to our own voice. For example, how many of you have heard a recording of yourselves and your voice is so thin sounding and you go, my gosh, do I sound that way to everyone in the world? Of course, the bad news is, yes, you do. Of course, today with video, it's an even scarier scenario. But the reason that that microphone sound to you is so different is that it's only picking up the acoustic information that's emanating from your lips. What you hear is not only that information that re-enters the ear canal, but the vocal cords within the skull are directly stimulating your inner ear via these bone conduction pathways, and that's why your voice sounds so different to you when you audit it naturally. When we put on a hearing protector, we can identify 4 sound conduction pathways to the protected ear, and they're illustrated in this slide. The first one is the one over which you have the most control. If you don't fit the device properly, or if it's a custom ear mold and it wasn't made well, there will be air leaks, and that can dramatically affect the noise reduction capabilities of the hearing protector. Pathway number 2 is a whole body motion of the hearing protector where it's oscillating like a piston within a cylinder. Pathway number 3 is a structural transmission, that is, the sound gets directly through the hearing protector. So for example, if you're wearing something like a wadded up tissue or a cotton ball in your ear, it's a very perforate material. Air can flow through it easily, sound can flow through it easily, and it won't block a lot of the noise. Normally, with a device designed to reduce noise, a hearing protection device in your ear, that is not a very substantial pathway. And number 4 are those bone conduction pathways that I referred to just a moment ago. In large part, the hearing protector doesn't have a lot of effect over those bone conduction pathways and how that energy gets through to the inner ear. Now, here's a very important effect that you should be aware of when you wear a hearing protector. It's called the occlusion effect. How many of you have had the experience that when you wear a hearing protector, your voice sounds different to you? It sounds bassy, hollow, resonant, boomy. I'm seeing about a half the hands, probably that same 58% that are wearing hearing protectors in music performances. If you wear a hearing protector and you wear it correctly, you will experience the occlusion effect. In fact, it can be used as a fitting tip to make sure that a device is well sealed. Let me demonstrate for you the occlusion effect. Now, wait until I tell you to do this, but what you're going to do is you're going to take your thumbs and you're going to press them over behind this little bump called the tragus, and you're going to press hard and seal the entrance to your ear canal. And while you're doing that, you're going to say the words boom, beat. Okay, cover your ears and say boom, beat. Did you hear the sound of your voice, how boomy it was in your ears? That is called the occlusion effect, and it's because the vibratory energy that normally can easily escape the ear canal is now being blocked by this object, whether it be a plug or your thumb, and caused to re-enter the ear canal and pass through the chain into the inner ear. So that energy is now recaptured. If you look at this chart, it explains how the occlusion effect works. Depending on how I seal the ear, I get more occlusion effect. If I seal it at its entrance with an earphone pressing against the ear or our thumb, for example, you see the occlusion effect is at its maximum. If I put an earplug more and more deeply into the ear canal, the occlusion effect reduces in magnitude. So this is particularly important if you're wearing a custom ear mold, for example, the ER15, the musician's earplug. If it's not well made, it will not be deep enough, and the occlusion effect will be greater. It will be more annoying. It will distort your perception of the sounds that you're trying to hear. So it's important, especially with those devices, that you have a very deep-fitting device to reduce this occlusion effect. It's something that people often find annoying, even if they're not musicians. I have a friend who says that she can't wear earplugs because when she wears earplugs, she can't breathe. But then again, without her glasses, she can't hear very well, so it's, you know. Her breathing issue is because she's wearing earplugs in noises that are not particularly loud because she wants to reduce the annoyance. And that does, through the occlusion effect, amplify all internally generated body sounds. And it's just not a sound that she's used to or comfortable with. So you can reduce this occlusion effect by fitting devices better or taking better ear impressions. The way we measure hearing protector performance is conceptually incredibly simple. It's exactly the way they work. We give somebody a hearing test, an audiogram. We measure the quietest sounds they can hear. We then put in the hearing protector and give them the test again. If the hearing protector has done what it's supposed to, if it's blocked those sounds, then we're going to have to raise the sound level for the sounds to still be audible in the protected condition. And this is called a real ear attenuation at threshold, or REAT type of evaluation. There's about a dozen other different methods that have been used over the years to examine hearing protector performance in more detail and under different scenarios, but this is the gold standard that is used worldwide. I'd like you to just hear a little bit of the types of sounds that are played. The room is generally a moderate-sized room. It has reverberant walls. It has a number of different speakers. And the sounds that we use are what are called third-octave bands of noise. So instead of listening to a pure or whistle-like tone, we present a noise band so that we can test the hearing protector over a wider range of frequencies. So here is a low-frequency third-octave band. This one is centered just about on middle C. So we would give a test with that sort of noise. Actually, we'd be pulsing it, but it would be that type of noise, and now you would do your threshold with and without the hearing protector. Here's a higher frequency signal. This one's at 4 kilohertz. You can hear that one sounds more like a cricket. So we cover a wide range of frequencies when we do this type of test. When we measure hearing protector noise reduction, we typically plot it in a graphical format. You've seen audiogram charts here today. This is, again, the same format of decibels versus frequency. Here's middle C at 250 hertz. Here's the upper end of the piano. Along this vertical axis, we have decibels. Normally, if we change the sound level by 10 dB, that is perceived as being twice as loud. Marshall gave you a 3 decibel demonstration earlier, which is an audible difference. In a laboratory scenario, the smallest difference that people can detect is typically 1 decibel. So it kind of gives you the scale. So here we're looking at a typical attenuation curve actually for an earmuff, which increases with frequency. These little yellow bars indicate the variability of the test data. The important point is that for many types of conventional hearing protectors, they will block more sound at the high frequencies than at the low frequencies. That means that when you wear the hearing protector, the world sounds muffled. It doesn't sound good, and if you're a musician, it's not the same frequency balance that you would have heard without the protector. So there are types of devices that can offset this effect to a large extent. Hearing protectors are labeled since 1979 according to a regulation of the Environmental Protection Agency. That regulation is currently under review and may well be changed in the next couple years. But it calls for the use of an outdated standard that is based on an optimum fitting of the hearing protector in a laboratory condition. So they are unrealistically high numbers. You will find these numbers on all products when you go to purchase them. People often say, I want a higher NRR, I want more protection. Especially in the music field, you don't necessarily want the highest NRRs. I can also tell you that in general, for non-technical people, I would say that NRR stands for not really relevant. When people ask me, how can I use the NRR? I tell them the only value in the NRR is the fact that it's on the package tells you that the device was designed for and tested for noise reduction. But it's such an inaccurate indicator, it's way less accurate than the early EPA fuel economy ratings were before the EPA improved them. So don't do a lot with the NRR. Just notice that it's there. This thing's really a hearing protector. Considerations regarding the NRR are that the range of them today are from about values in the single digits up to the low 30s. Differences in the NRR of a few dB are absolutely inconsequential, and as I said, don't spend a whole lot of time worrying about it. Somebody who wears the device absolutely perfectly can begin to approach those sorts of values, but if you're looking at, I've got a group of students or a group of workers who are wearing the device, as an aggregate, they will never get these types of values. There's another important effect with hearing protection, which is noise, like radiation, is a dose effect. So it's not just the level, but it's the duration of the exposure. It turns out that if you are wearing a hearing protector that's very effective and you simply fail to use it for a short portion of your noise exposure, its effectiveness drops dramatically. It's a logarithmic effect. We're looking at a chart here of the time-corrected NRR. So this is the effective noise reduction during a period of exposure versus the percentage of time that the device was actually worn. And the parameter here is the presumed or the assigned noise reduction of that device. This was drawn primarily for an industrial scenario. You would look here at a worker who's exposed 8 hours a day. If they fail to wear the device for simply 15 minutes out of an 8-hour shift, that 25 dB NRR drops by 5 dB down to 20 decibels. So for short periods of disuse, you can dramatically affect the protection that's obtained. In the scenario with music rehearsals where they're shorter time periods, this is still important, but of course we have to translate those doses to the shorter time frames. However, for someone who's an instructor, who as Marshall was talking about is exposed many hours a day, many days a week, it's much like the industrial scenario. They need to be looking at wearing it all the time, not just a portion of the time. If, for example, they were wearing it as little as half of the time, then regardless, they could have an infinite hearing protector and it would only be giving them an effectiveness of about 5 decibels of noise reduction. Sometimes questions are asked about how much noise can I block. I mentioned that there are these bone conduction limits. They are shown on this chart here, as I said, in the range of 40 to 50 dB. People sometimes wear a plug and a muff together. I could hardly imagine a scenario in the music world where one would need to do that, but if you're looking at those for other types of hazardous exposures, you can't simply add the protection from the two. They don't add because of the limits of the bone conduction and some other physical factors. So you can see here's an earmuff and an earplug. They both give about 30 dB, but the combination doesn't give 60. The combination gives, at this frequency, only about 39 decibels. When I wear a hearing protector, I do tend to hear better in noise levels. In high enough noise levels, I can actually hear more clearly. Now, this is not for the person who's potentially playing the instrument, but as I'm listening to music or listening to speech, I can actually hear better in very high-level noise with a hearing protector. And the reason is that the ear above the level of 85 dB begins to distort. That shouldn't be a great surprise. We've heard that noise levels above 85 dB are hazardous to the hearing. Above 85 dB, the ear does not hear as clearly. So if I can limit those levels, if I'm looking at listening at 105 dB and I can bring those levels down into an area where the ear doesn't distort, it's much like this case with a visual analogy. I'm on the beach, it's way bright, it's much brighter than the visual stimulation that my eye can easily adapt to. So I put on a pair of sunglasses and I bring that stimulation down into the range where the eye can function more effectively. So, for example, sound installers who are taking a listen to the sound systems that are being broadcast at 110 and 115 dB can much more easily hear the distortion in those systems if they put in a hearing protector and bring those levels down into the range where the ear can hear more clearly. The catch is that the sounds have to be loud enough, and it's at about 85 dB where you have this trade-off. Below 85 dB, certainly the hearing protector will affect your ability to hear, and so music with a wide dynamic range, if it's right in the 85 to 90 range, certainly some of those quiet sounds will get quiet enough that the hearing protector can affect one's ability to hear them. So there are specialized types of devices that I want to spend a few minutes talking to you about. We have uniform or natural sounding attenuation, which means let's get rid of this muffling effect. Instead of our typical attenuation curve, let's have something that attenuates equally at all frequencies. Let's look at moderate attenuation. Let's not block too much noise. We can look at tuned or vented attenuation, where we purposely put a hole through the hearing protector and let some sound in at the low frequencies and reduce the overall protection. And then we can look at what I mentioned briefly was the active noise reduction. So a few examples. Now, this is not a specialized type of hearing protector, but I'm showing this at the outset of this section because these are custom ear molds, and many types of specialized products are built into custom ear molds. For those of you who might be numismatists, coin collectors, who were doing this years ago, that's a mercury dime, which I've used there for scale. Kind of shows you this particular slide's been around for a while. What I have here, and the reason I like to use this slide, is that these are 5 custom ear molds, all made for my right ear canal, all made by people who purportedly were expert in making custom ear molds. The portion of the custom ear mold that goes into the ear is the portion that's highlighted by those arrows. You can see that those are 5 radically different impressions of what my ear canal looks like, and the only one that's correct is the orange one in the upper right. And these were all made by either otolaryngologists, audiologists, or representatives of the companies that manufacture these products. So it is difficult to make a custom ear impression. In fact, that's often why with hearing aids you end up having remakes and refits, because that hearing aid impression was not made adequately. So it is important that you get a full and deep impression on your custom ear molds. This is one of my favorite products. A fellow by the name of Meade Killian brought this to market. His mentor, Elmer Carlson, invented it. And every day I wear this product, I thank Meade for having introduced it. It's called the ER15, the musician's earplug. It's a custom ear mold that has a big hole through it. And that hole is capped by that little plastic button, which has what we call an acoustical network in it that adjusts the frequency response to that hearing protector. It also uses some other interesting acoustical tricks, such as where the inlet is to that hearing protector, which is in a region of the ear where it benefits from the ear zone amplification. So this device ends up giving you essentially a flat 15 decibels of attenuation at all frequencies. It's a neutral sounding device. When I first wore one about 15 years ago, I thought I had a defective hearing protector in because it didn't sound like I'd never listened to something that would just turn the volume down 15 dB without putting in the high frequency filter and turning down the treble at the same time. So it took a little bit of getting used to that really I was getting the protection I was supposed to. Probably the biggest disadvantage of the ER15 is it's going to set you back about $140 to $150 and 2 visits to an audiologist. And everyone would like to visit Marshall, but I don't know if you want to visit him twice and give him 150 bucks. If it's important enough to you, you definitely want to. But for your students who probably can't afford that, they may want to look at a lower cost option initially, and there are pre-molded devices such as this ER20, which is available from a couple of different companies. And this device also has a hole through it, also has an acoustical network, but it doesn't do quite as good a job. You might expect that if you pay $12 versus $150, that there might be a little more performance in the $150 item. And so here I show you the attenuation for a range of different products. Here is the ER15, which is truly phenomenal. I think, you know, for the average person, that is a perfect 15 dB essentially at all frequencies. The blue curve is the ER20, and you see that it is not as flat. It changes about 10 decibels over the audio range there. For most people, that will be quite adequate, but it is clearly not as high fidelity an instrument. And also for most people, it's not quite as comfortable. It's a flanged earplug, and many people prefer the comfort of a custom ear mold. For comparison, you see a foam earplug, which has dramatically more protection when it's well fitted. You see a pre-molded earplug. And by the way, if you were going to be packing cotton very tightly into your ears, which could be of some benefit, it does mute the high frequencies, 15 decibels or so, but it's not really a conventional hearing protector. It's not as reliable, and it's giving you virtually no protection in the low frequencies. So that gives you an idea of the types of protection you can see. In the ER line of products, by the way, for those of you who use them or recommend them, you're aware that there's a 9 decibel button as well as a 25 decibel button that are available in that product. Excuse me, the green curve is the 25 decibel button. So you can plug in different buttons and get different degrees of protection with that device. There are other types of vented protectors. You can simply take a custom ear mold and put a hole through it. There are also devices such as the one in the upper left here, the Ergotech Verifone, that actually has a variable valve assembly where you can screw adjust this valve to let a predetermined amount of sound through. And a very new product on the market called the Sonomax, which is quite interesting because in this case, unlike a typical custom ear mold where you put a dam or a block in the ear and then shoot a gooey liquid like a runny peanut butter into the ear after that, and that sets up and makes your impression. In the case of the Sonomax, you put a balloon or a bladder in the ear, and then with a hypodermic, you inject the liquid material into that bladder, and it inflates, so it becomes a custom ear mold with a skin on it. It's not quite as good a fitting custom ear mold. It has some limitations, and it's still a product that's being developed, but it's a very interesting approach. It allows the insertion of a leakage pathway, which you see here, and also the way in which they fit it, they can actually measure the noise reduction of the device as it's fitted to you to ascertain the amount of protection that you are going to obtain with that particular fitting. So there are some higher tech ways to do this. What you want to keep in mind is that with vented custom ear molds, they always slope with frequency. So they're kind of like the cotton we saw. They let in more low frequencies, they block more high frequencies. It means they don't have as neutral a sound characteristic, but there may be times, for example, if you're a woodwind player where more of your personal instrument's energy is in the low frequencies and you want to hear that, but you might be near some higher frequency instruments, horns or percussion, which has high frequency energy that you want protection from. It can give you the balance of letting you hear your own instrument's sounds more clearly and blocking some of the other instruments that are a little bit too loud for you. To review briefly and provide a little more information, we talked about the occlusion effect. With a deeper fitting earplug, such as a foam plug, you get less occlusion effect when it's in deeper. It also tends to be more comfortable. And this family of curves here shows you what happens to the attenuation as you fit the device more deeply. So a very interesting thing occurs. Not only is the occlusion effect changing, but you can see that a deeply fitted foam earplug is essentially a flat attenuator. A shallowly fitted foam earplug gives you very little low frequency attenuation and a lot of high frequency attenuation and will sound quite muffled. So a foam earplug can change its characteristics dramatically depending on how you fit it. The downside of the foam for the musician is that even when it's a flat attenuator, that's 40 decibels of noise reduction. That's way more noise reduction than most musicians would actually want to obtain. Marshall mentioned a case earlier with a drummer wearing a foam earplug who didn't hear enough of his drum sounds, so he's overplaying. So you want to be cautious when you're using those amounts of protection. A key concept in fitting any insert earplug is what you see this fellow doing here. It's called the pinapole. You're reaching over your head, so it's a kind of an ungainly process. I'm not doing it this way. This doesn't work. The reason this doesn't work is that most ear canals are forwards and upwards. I want to insert the earplug with the hand on the same side of the head as that ear canal so I have maximum dexterity and mobility. If I've got my wrist twisted and I'm trying to adjust the earplug while I'm doing this, I can't work with the earplug as effectively. So I'm pulling from behind as I come at the ear with a hand on the same side. And by the way, many people just take their fingers and lay it on their ears. That doesn't work. You're grabbing this pinna and pulling it outwards and upwards in the direction that it grows. So I want to mention just briefly active noise reduction technology. Some of you may be familiar with it because it is a very high-tech approach. Also, Bose Company, that has an A&R product, is probably the biggest advertiser of those types of products worldwide. They have some specific target markets, and one of them is not protection from hazardous noise for occupational or musicians' exposures. Their only application for A&R for hazard reduction is in the military for people who drive tanks, and fly airplanes. For our applications, it really is not apropos. The way ANR works is that there is a noise-sensing mic in the cup that will pick up the sound that gets through the cup, and so it generates an anti-noise signal that's exactly a mirror image of the noise signal, and if the two of them are aligned perfectly, you get cancellation. For that to occur, it requires an incredible timing between the two signals, and this relates to the geometry and the wavelength of the sound. And it turns out that this can only be effectively done in the low frequencies. ANR does not work above about 500 hertz. So 1 octave above middle C is about as far as ANR will work. In the high frequencies, it's going to do nothing for you. The principal application for you all is going to be transportation. You would like to reduce the sound levels in an aircraft when you're flying, or maybe your automobile, and you'd like to be able to hear some music at the same time. So these sorts of devices, and here you see 2 of them, give you an ANR noise reduction and allow you to play some music at the same time. The one on the left, which was an open ear device, you see gives no reduction until the ANR is turned on. The Bose device is very interesting. The ANR off gives little low frequencies, but about 30 decibels in the highs. When you turn on the ANR, you can see that you now get a much flatter attenuation curve. And in fact, that device is a very reasonable device if you're flying on an airplane and you want to listen to the movie. What I would suggest, though, is that there's a lower cost alternative, which has nothing to do with ANR, which is the plug that Marshall mentioned earlier for musicians to use as an ear monitor. The ER6, you can see, gives substantially more protection than that ANR device. It has the same fidelity or better. It costs half as much, and by the way, you can carry it in your pocket. You don't have to carry it in a bag. However, you may not be an earplug type of person. You may not want to put things in your ears. You may want to wear an ear muff. So there's ergonomic trade-offs between the two. But the principal application for ANR for most people who aren't in the military is really nuisance noise reduction, not hazard noise reduction. In closing, I would like to just emphasize a point that few of us talked about earlier here today, which is tinnitus. Hearing loss is certainly a horrible affliction and can affect our ability not only to play music, but to communicate with those we love. The problem is that so often when you turn off the sounds you want to hear, you replace them with this sound in your head that you don't want to hear, that you have no control over. And for some people, it is severe enough that they consider suicide in extreme cases. Tinnitus is an awful affliction. You could liken it almost to a sound burn, we could call it. It may be due to overstimulation of the cells, just like your skin talks to you when you get sunburned, your hair cells can talk to you when you get noise burned. There are other causes of tinnitus. It's a good personal indicator. If you don't generally have tinnitus, you're now in a noise or music, and when you leave that exposure, your ears are ringing. That's an indication that that noise was too loud for you. I'd like to play a little tinnitus demonstration. For those of you who aren't afflicted by it, let's let you just have a moment of experiencing tinnitus in your lives.
Here is an example of one type of tinnitus. The onset of tinnitus immediately after exposure to noise is a warning sign. If you don't protect your ears from noise, the temporary tinnitus you initially hear can become a permanent, constant, incurable blight. Imagine having a bright red spot in the middle of your visual field, one that never, ever goes away.
Here's a hearing protector that came out in 1927. The Elliott Protector shields the ear from dust, noise, severe vibration, prevents deafness, headache, and restores impaired hearing. Well, I wish I could offer you that product today. There are some good hearing protectors on the market, and there's a wide variety from which to choose. There's really no reason for people to have noise-induced hearing loss except for the accidental, incidental exposures such as explosions and other unexpected events. So spread the word about hearing protection to both your students and your faculty members, and let's make sure that the world stays a place in which we can all enjoy our hearing senses. Thank you. Are there one or two questions? We do have a summary that we need to present, but if there's a couple questions on hearing protection, we could take them now or proceed to our summary.
We did have one audience response hearing question. What should be the first line of defense for prevention of hearing loss in an ASM schools? Okay.
Okay, we're now going to try to give you some recommendations from our committee. We met last night and reviewed the kinds of things that we have told you today, knowing that we were going to say those things. And these are the basic recommendations, and I'll expand just a little bit on these as we go along. The basic recommendations that we have for you to protect your students' hearing, and your own as well, are education, hearing screening program, monitoring music levels, and protective strategies. In education, we feel that we should develop materials for faculty and students concerning the effects of noise or music. And you remember that although the public may differentiate between music and noise, they're both sound, and it's a sound level that's a problem. I don't care if you listen to The Who at 110 or you listen to Beethoven at 110, it's going to hurt your ears. So the effects of noise music on hearing, the associated consequences, and methods of protection. All of those have been reviewed to some extent in the presentations that we've given you today. There's a lot of material on the web that you could get together for students, and we think that this could be done relatively easily. Hearing screening in most universities and colleges and high schools as well. You can do hearing tests on your students when they begin the music program. So we recommend an entrance baseline audiogram. That is, when the student starts taking music from you, at that point, get a hearing test and see what their hearing is like. Do a tinnitus assessment. There's a lot of controversy on how accurately tinnitus can be measured, but at least if you're using the same assessment procedure pre-exposure and post-exposure, you have an idea of whether it's gotten worse or not. You should monitor the hearing of your students and you on an annual basis. Every year they should get a hearing test. This goes along also with OSHA guidelines, NIOSH guidelines, ISO guidelines. Everybody's saying the same thing. If you notice a change in hearing, you should have your hearing tested more often than once a year, but otherwise at least once a year, because as we have said in this presentation, hearing loss is slow growing, it's insidious. You may not notice that you've had a hearing loss at all, but if you test your hearing periodically, you will be able to tell whether there has been a change or not. Now, if all the audiologists will close their eyes and close their ears, I'll tell you a quick, cheap way to do this without an audiogram. The audiogram is absolutely the best way. Rub your fingers right by your ear, and if it changes from time to time, you will notice that your hearing is changing. That's a quick and very dirty test of hearing. We should also develop and implement procedures to assess and respond to changes in hearing. If we see a student or you who have changed your hearing, what do we do about it? And so we need to produce some procedures. We're probably going to recommend staying away from the sound as much as possible, cutting down on practice time perhaps, being careful about performance, and maybe wearing musicians' earplugs, etc. There are lots of ways that you could respond if you have noticed a change, rather than just simply saying you can no longer do music. You don't want to have to say that. Another thing that we can do is monitor the music levels. You need to see what the levels are both in practice and performance activities. We've already alluded to the fact that the way you practice may be different than the way in which you perform. You don't perform at the same level necessarily that you may practice, at which you may practice. So you need to make measures of the sound level overall in the environment, and then dosimetry, which is a measurement of the individual's exposure to sound. Usually wearing a microphone and a dosimeter where the microphone is close to the entrance of the ear canal, and seeing what kind of dosage of sound the person has during the course of a day. That's the best way, but it's more expensive. There are protective strategies that you've also heard today: hearing protection, administrative controls. This means things like cutting down on the amount of exposure, environmental modifications, and you've got a lot of examples on that, some architectural, some positioning, some barriers. And finally then, who should be accountable? And we believe that this should be part of NASM accreditation procedures. We believe that oversight should be included in the kind of evaluation that NASM does over your programs. And if they require that this type of monitoring and accountability is carried out, we believe that that will help you and it will help your students. Thank you very much. We have 2 minutes. We have 2 minutes, so if we have any other questions, we'll be happy to attempt to address them. Otherwise, you can start drinking. I know you can start joining one another in reception earlier.
While you're thinking of your questions, we'd just like to point out that I have a few samples up here of the high-fidelity hearing protector, the pre-molded one. Didn't have enough to put in all the bags, but if you'd like to come up, there's a dozen or so here, and you'd be welcome to grab one of those on your way out of the door.
Hi, just a quick question, I think. Janet Jensen, University of Wisconsin-Madison. One of my colleagues from UW Hospital sent me an article, knowing I was coming here, to the effect that left and right ears process sound differently, and that this had some implications for how we correct hearing loss in children particularly, but also in musicians. Is this a well-researched phenomenon, or?
Yes, it was researched 20 years ago. Despite what the New York Times said, this is not a new concept. It was first described by Kimura, right? In which she found that there is a very slight and subtle difference in the way the ear processes voice, speech, and music type stimuli. As far as we know, that difference is really quite slight. You can demonstrate it, but it's very difficult to do it, and it's not clear how important that is. So at this point in time, I don't think we have any evidence that would say that you need to do differently for listening to music than you do listening to speech or anything else. Okay. It's been done before, but as I tell my students, you know, just because it wasn't written in 1999 doesn't mean it didn't exist. You people in music have a much better appreciation than I think of that. You know, think about what would happen if we said, well, you can't play any composers that composed before 1900, right? Well, we seem to do that in our field. If it was written before 1990, it doesn't exist. So it's an old concept. It's true, but it's a very slight difference as far as we know. Okay? But whoever said the New York Times read the literature? Any other questions, comments? Well, let's go receive ourselves.